um, Physics, chapter 23, theory video 6, capacitance of isolated bodies. So now we discussed that the capacitors can be charged, and as a result they have the ability to discharge their charge under different circumstances. However, now we have seen that any object can be charged by rubbing. So that means all bodies have capacitance. So even our bodies have capacitance. So for example, if you were to remove a silk clothing that you have worn for some time, if you were to remove that, you would hear the crackling sound that you would get. That is due to the discharge of charges. That means there would be sparks generated. So this we can get rid of these charges that develop by discharging it using by touching an earth metal object. There would be a spark that would generate. So this charge of a sphere, or else the capacitance of a sphere we can obtain by using this relationship. V equals 1 upon 4 pi epsilon O into Q upon R, and then we can relate it to C equals Q upon V and obtain the equation C equals 4 pi epsilon O R. So that is the capacitance of a sphere, C equals 4 pi epsilon O R. So these two equations are going to be quite important. You need to remember them both. Then moving on, we have to learn about charge and discharge of capacitors. So as we discussed in one of our earlier lessons, you can see that when we connect this circuit, P circuit, the current from these power sources will come and charge this capacitor, right? So please remember, so these are power sources here, and the two equal length lines provide us the capacitor. But when it is connected to the Q circuit, so there is no power source, it is not going to get charged, but it is going to get discharged. So what happens is, initially when this is being charged, there would be a higher current flowing through initially, but with time it will reduce and come to 0. But when it is getting discharged, also the same thing would happen. It would discharge at a higher rate at the beginning and later on slowly come to 0. And we can see in the using this microammeter, we can see when the current is when it is getting charged, when the capacitor is getting charged, the current comes in one direction. When it is discharged, it goes in the other direction. So these are little details that we need to remember. And we get this type of a graph when we charge or discharge through a resistor. Initially the rate at which the charge drops is high, then later on it reduces. This is referred to as the exponential decay, and in in radioactive decay also it will show an exponential decay. So that means there is a power. We will come to deal with it in our equations later on. So here we have a relationship here, x equals xo, that is the x is the dependent variable, then xo is the initial dependent variable, then e to the power negative ky. So this relationship should be understood. K and xo are going to be constant, and e is the exponential function. So this exponential function is would have a value of 2.711828. We are going to use this e in the next in our next equations. When you do this question number 22, I would suggest that you pause the video now and attempt this. If you have any questions, please raise questions. I will explain it further. But when you do this question number 22, you would be able to understand why current gradually reduces, and because you will understand the current reduces because it takes the charge of the plates. Now, in our earlier situations also, I suppose you can remember, negative Q charge arrives and the positive Q charge would be formed on the other, repelling another negative Q charge. So that is how it happens. Then if you increase the if you change the resistance in the circuit, you know there is no change in the potential difference, but there will be a change in the current. So as a result, when you increase the resistance, that means there is lesser current. So as a result, the charge would flow off more slowly. So that means it will take longer to discharge. But if you decrease the resistance, that means there will be higher current, and as a result, it can discharge more quickly. So then what would happen if the capacitance is increased? When you increase the capacitance, you know that more charge can be stored. As if there is more charge, it will take more time to discharge. So there are two factors that affects the time that it takes for for a capacitor to discharge. Those are resistance and capacitance, and we take those two in this relationship. Tau, that is tau is the tau is the time constant, and this time constant is referred to as RC, resistance into capacitance, right? This time constant is going to be important when we do our calculations. Once again, it will be discussed in the next parts, right? The time constant RC, the units are going to be the second. I would suggest that you do that. Do the question and prove that it is seconds. Then you will be ready to do the final questions. So now there are three equations that we can use for the exponential decay of charge on a capacitor. One is I equals IO, exponential decay value, negative T upon RC. So E, that relationship should be, we should understand this. Then here, because current V equals IR equation, because V is directly proportional to I, and because current is directly proportional to V, then at the same time V is directly proportional to charge across the plate, Q. So as a result, we can develop three equations. V equals VO EXP, negative T upon RC. Then Q equals QO EXP, negative T upon RC. So in all of these three things, you need to remember the left hand side, IVQ, is the individual, the current, voltage, or the charge. But IO, VO, QO, they all stand for the initial current, initial voltage, or initial charge. So depending on what the details or the data that they have provided, we would have to use one of these three equations. So now let's look at the fourth example. There is a potential difference across the plates of resistor, plates of a capacitor of capacitance 500 microfarads. So you know how to convert microfarads into farads, 10 to the power minus 6. So then is 240 volts. The capacitor is connected across the terminals of 600 ohm resistor. Find the time taken for the current to fall to 0.10 amperes. So they are asking the final current is 0.10 amperes. So the left hand side is going to be 0.10 amperes. Then we have to find out what is the initial current. We have the details. IO equals V upon R, V equals IR equation. V is 240 divided by 600 would give us 0.40 amperes, right? Then we need to find the time constant. Tau equals RC 600 into 500 into 10 to the power minus 6. Resistance, they have given it to be 600 ohms. 600 because capacitance has been given in microfarads, we have to convert that into farads. 500 into 10 to the power minus 6, then that gives us, tau gives us 0.30 seconds. That is not the answer, that is the time constant, that is the time constant, that is RC. So we use the equation I equals IO exp negative T upon RC. We get 0.10 0.40 exp, it does not, the exponential rate does not go away, negative T upon 0.30. Then we have, we divide either side by 0.40, 0.40 gets cancelled out on right hand side. Left hand side you are left with 0.25 exp negative T upon 0.30. This E, as you can remember, E stood for, here in this part, E is the exponential function. So this exponential function, as you can see in this relationship, it is exponential, means there is a power involved. So here this exponential function E can be described as the antilog of the natural logarithm, antilog of natural logarithm, such that e to the power x is equal to x. So that is a function that we have learnt. Then we take the natural logarithm of 0.25 is equal to negative t upon 0.30, right? So this calculation, this step is very important, right? You do not have to know all the details, but if you can remember this step, natural logarithm of 0.25 would give you negative t upon 0.30. Negative logarithm of 0.25 is negative 1.386. Then you get the final answer to be 0.41 seconds. I hope you understood. If you understood, you can do question number 24. If you have any doubts, please ask me questions. Right, so the summary is, there are many equations that you need to remember from this lesson. The summary is, we know that capacitors are constructed or built by two metal sheets separated by an insulating material. They would store an equal and opposite charges on either plate. Then the charge stored is directly proportional to potential difference. So we obtained an equation Q equals Vc. Q stood for the charge, V stood for the voltage, and C stood for the capacitance. Then we define the capacitance as the charge stored per unit potential difference. Then a farad is a coulomb per volt. 1 farad equals 1 CV to the power minus 1. Then capacitors store energy. We have several equations for this. W equals half QV, which is equal to half CV squared, which is equal to half Q squared upon C. So these formulas you need to remember. Then formula W equals half QV is obtained or is deduced from the area under the graph of potential difference against charge. Then when we connect, we discussed about connecting parallel and series. Unlike the resistors, in parallel form we get C total by adding C1, simply adding the values. But in series, 1 upon C total gives us 1 upon C1 plus 1 upon C2, 1 upon C3. Then when we draw graphs for discharge of current, charge stored, and potential difference across a capacitor, all would be examples of exponential decay. So that means there is a power involved. The time constant for circuits containing capacitance and resistance is tau equals CR. Then when we discharge a current, charge stored and potential difference across a capacitor are all of the form x equals xo exp negative t upon rc. So the x could be uh, I velocity o q. So these values and these equations you need to remember and by heart. Go through the lessons and see whether there is any doubt that you might have. If you have, please raise them.